I welcome you all for this presentation. In this presentation, we are going to discuss about IEEE 802.11 and wired equivalent privacy. This is the overview of this presentation. Introduction to IEEE 802.11, Wi-Fi Alliance, IEEE 802 Protocol Architecture, then 802.11 Wireless LAN Security, then wired equivalent privacy, then web components, how web works, then web authentication, web flaws and vulnerabilities, followed by summary of this presentation. What is IEEE 802.11? This IEEE 802 committed for the is mainly committed for the LAN standards, and this IEEE 802.11 is formed in the year 1990s, and it is a charter to develop a protocol and transmission specifications for the wireless LANs. So in this presentation we are going to discuss about the wireless communication, that is how we are securing the wireless. Nowadays we are having wireless only, mobile devices, many smart devices are there. So what is the foundation of this wireless? Then only we know how to secure those things. So this IEEE 802.11 is for the wireless LANs. Since then, demand for wireless LANs at different frequencies and data rates has exploded, and it's seen ever expanding list of standards are issued about this IEEE 802.11. So mainly 802 is for the LAN standard and 802.11 is for the wireless LANs, and we are having many things. 802.11i we are having, so many things we are having in, and for each and every standard, for each and everything we are having a standard, and how to protect all those things, because privacy and security is very important, and this is the last topic in our information security course. So finally, we are just having a basic foundation about how to secure the wireless local area networks. So you know what is Wi-Fi? It is a wireless fidelity. So 802.11b was it's the first broadly accepted standard, and it is a wireless Ethernet compatibility alliance industry consortium is formed in 1999. Actually, 802 is becomes the standard in 1990s. Then this wireless 802.11 is becomes a standard in the year 1999. It is mainly this wireless Ethernet compatibility alliances to assist interoperability of products. Nowadays, then only in the 90s only this wireless networks or wireless communications become very famous. So how to develop more products or manufacture many products in order to have interoperability among the connected products. Nowadays everything is smart devices, so everyone is having the mobile devices. Nowadays we are having many equipments, even mouse is wireless, keyboard wireless, many things we are having wireless. So how the communication happens, and while communication happens we have to secure in an efficient manner. So how to provide all interoperability among the various wireless products, that we have to know. So that they have formed an alliance, that is industry consortium was formed in the year 1999, and it is named as Wi-Fi Wireless Fidelity Alliance afterwards. It created a test suite to certify the interoperability initially for 802.11b, then later it was extended to 802.11g. So you see where many variations are there. 802.11 A, B, C, D, G, I, likewise many things we are having in. So you please go through for each and everything what it means. And it is concerned with the range of wireless LAN markets including enterprise, home and hotspot. Next is IEEE 802 protocol architecture. So we know here we are having the physical, medium access control and logical control. Physical and data link layer is there. Under data link only we are having the logical link control as well as medium access control. General IEEE 802 functions include, for the logical link control it handles flow control as well as error control, and in the medium access control it assembles data into frames, then addressing, then error detection and medium access control. So medium access, everything. These are the functionalities of medium access control. And coming to the physical, you all of you are familiar with that. That is encoding, decoding of signals, bit transmissions, reception, and with respect to the transmission medium. and the specific functions with respect to 802.11. This 802.11 is for the wireless local area network. So the specific functionality of this 802.11 is it mainly the physical and whatever the things with respect to this wireless we are handling in. There we need to understand the physical as well as the data link, mainly the physical as well as the medium access control. So the specific functionality of IEEE 802.11 includes with respect to the medium access control, it provides reliable data delivery. Then wireless access control protocols. All the wireless access control protocols are in this layer only, medium access control. And coming to the physical layer, the frequency band definition and wireless signal encoding are there. These are the network components and architecture in the distributed system with respect to the wireless environment. So here you know basic service set is there, BSS is there. Then we are having the distribution system there. So the basic service set is connected. We are having many wireless connections, right? So here we are having all those nodes are there, and all those things are connected to this basic service set. Then it is connected to the distributed system. These are some of the services with respect to 802.11. That is, services include association, authentication, deauthentication, disassociation, then distribution, integration, MSDU delivery, privacy as well as reassociation. Here you see the association, disassociation as well as reassociation. So the providers for each and every service is given, as well as each and every service as well as the provider supports what. For that we are having used to support column, that is MSDU association service with respect to the provider distribution system supports MSDU delivery. Likewise for all the services we are having the support also for this 802.11. Next is mainly what is our ultimate aim? We need to know how to secure 802.11, that is how to secure the wireless LAN. For that only we have seen just an introduction about 802.11. You have to know what is 802.11, then only we know how to secure the wireless LAN. So here wireless LAN security, that is wireless traffic can be monitored by any radio in range not physically connected. It is a wireless, so it is not physically connected. Originally 802.11 spec had security features. For that only we are having wired equivalent privacy. So that only I have given in this title like IEEE 802.11 and wired equivalent privacy. We are going to discuss about the wired equivalent privacy only. It is algorithm to secure the wireless LAN. But found this contained major weaknesses. So this contained major weaknesses. 802.11i task group developed capabilities to address wireless LAN security issues. Those are Wi-Fi Alliance, Wi-Fi Protected Access, WPA, and the 802.11i. That only I already do. It's a very famous for 802.11 wireless LAN security. That is, it's a robust security network. 802.11i is a robust security network. So for each and every the variation of 802.11 is for some specific purpose. This 802.11i is for the robust security network. So in order to avoid the weaknesses in the wired equivalent privacy, we are going in for this this Wi-Fi Alliance as well as robust security network. Let us see what are these. So 802.11i RSN services and protocols with respect to the RSN, that is robust security network, with respect to services and protocols. You can see these are the services available with respect to RSN, that is access control, authentication and key generation, then confidentiality, data origin authentication and integrity, as well as replay protection. For each and every, in order to provide these services, there are different protocols available for each and every services. So the protocols for access control is IEEE 802.1 port-based access control. Then for authentication and key generation, we are having extensible authentication protocol. And for confidentiality, in order to provide these services, we are having two protocols, TK-IP as well as CCMP. Then coming to the cryptographic algorithms, the services with respect to the services, that is main services for the cryptographic algorithms are confidentiality, integrity, authentication as well as key generation. You all of you are aware of that. So for each and every services, we are having the algorithms. Like for confidentiality, we are having RC4. Then another thing is AES-CTR counter mode. We have discussed that in third or fourth unit. Then NIST key wrap is there for confidentiality. Then in order to provide integrity and data origin authentication, mainly we have to use the hashing algorithm. So that only we are having the HMAC SHA-1, then HMAC MD5, next TKIP, Michael Mick that we didn't see, then AES CBC MAC that we have discussed earlier. Next is for key generation, we are again having HMAC and SHA-1 and RFC 1750. These are the cryptographic algorithms with respect to this robust security network. Next is the phases of operations in this 802.11. So we are having a STA, then we are having AP. What are these things? We have seen already in the communication network or wireless LAN. So here first phase is discovery. First we have to discover. Suppose we are having a mobile. So where we are getting a signal, first we have to discover it. Suppose if you are connecting to a Wi-Fi, it will discover first. So the first phase is discover. Then only we are just giving some password protected thing is there, means we have to give the password, that is authentication. For that only we are having the password. Next phase 3 is the key management. Phase 4 is the protected data transfer. So here before transferring the data in a secure manner, we are having 3 steps above that. First is we have to discover, then we have to perform authentication, then we have to do the key management, then only we are just transferring the data in a protected manner, then connection termination. So these are the 5 phases of operations in this 802.11i. Next is the 802.119 discovery and authentication phases. Here also we are having a diagram like the communication, how it happens between the STA as well as the AS. That is, station sends a request to join the network. That is, first the probe request is sent to AP. Then AP sends a probe response to STA. Here AP sends possible security parameter, then security capability set for the security possible policy. Then the station sends request to perform the null authentication, because the next step is we have to authenticate. So open system authentication request. Then for that this AP performs null authentication, that is open system authentication response. Then association, with respect to association, the STA sends to AP. Then AP sends a response to the STA, association response. Then the data transfer happens, protected data transfer happens. So 802.1x control port is blocked. Then the AP sends 802.1x AP request and this STA respond to that. Then only AP sending the access request to the AS. So we are having the extensible authentication protocol exchange from STA to AS. Afterwards only we are having these things. Then this AS accept EAP success key material, then that is sent from AP to STA. Finally, the control port is blocked. So the termination happens. Next is the 802.119 key management phase. So how the keys managed, that is how the pairwise key hierarchy is there and group key hierarchy is there. So see here we are having the pre-shared key, then AAA key is there. That both forms the pairwise master key. Both the key, pre-shared key as well as the AAA key. It is for authentication purpose. So both forms the pairwise master key. Then from that we are having the pairwise transient key. Then it is split it into 128 bits of EAPOL key, confirmation key, then encryption key as well as temporal key. So this way this is the pairwise key hierarchy formation. That is, from pre-shared key to the authentication key, a pairwise master key is formed, then transient key is formed. Again it is split into confirmation key, encryption key as well as the temporal key. Coming to the group key hierarchy, we are having a group master key, then we are having the group temporal key. Next, how to manage the key manage the key in 802.11i, because we have seen the hierarchy, group hierarchy. what are the keys available with respect to 802.11, how these keys are managed between STA as well as AP, because the communication happens between STA and AP up to the key management phase. Before data transfer, we have to manage the key. So for that, only STA and AP are involved. So the steps already we have discussed something with respect to the key. Here how the data transfer, that is the key management phase, happens, it is given. Next is the protected data transfer. After key management phase, we are having the protected transfer phase. Here we are having two schemes for protecting the data. One is the temporal key integrity protocol. Here the software changes molded only to the older wired equivalent privacy, and it adds 64-bit Michael message integrity code. MIC code is there. That is the Michael message integrity code, and it encrypts MPDU plus MIC value using RC4. Another thing is, another scheme is counter mode, that is CBC MAC protocol, that is called as CCMB. It uses the cipher block chaining message authentication code for integrity. So in all the security part, whatever the cryptographic algorithms we have learned, those algorithms are used in an appropriate manner. So basic cryptographic algorithms you need to know, then only we can utilize. If we want to secure anything, that is either the wireless devices or the mail or web or internet or transport layer, anything, if you want to secure it, even the file or database security, if you want to do, we need to utilize what are the cryptographic algorithms. If it wants to provide confidentiality, then we have to utilize the cryptographic algorithms. Otherwise, if it wants to provide some authentication, some hashing algorithms, we have to use. And this uses the CRT block cipher mode of operation. Here 802.11 is pseudo-random number function. Here using HMAC SHA, the pseudo-random number is generated using this pseudo-random function. And for generating the pseudo-random function, a counter mode is used because it is incrementing +1, so counter mode is used there. Next is the wired equivalent privacy. The original native security mechanism for wireless LAN is wired equivalent privacy. It provides security through 802.11 network, and it is used to protect wireless communication from eavesdropping. That is in order to provide confidentiality. Then it prevents unauthorized access to a wireless network, that is using access control, and it prevents tampering with the transmitted messages, and it provides users with the equivalent level of privacy in these wireless networks. And mainly, in order to provide integrity, it appends a 32-bit CRC checksum to each outgoing frame, and in order to provide confidentiality, it encrypts the frame using RC4 stream cipher. How it encrypts using RC4 stream cipher means 40-bit standard or 104-bit enhanced message key plus a 24-bit initialization vector, random initialization vector is used in order to provide confidentiality. The initialization vector as well as the default key on the station access point are used to create the key stream, and this key stream is used to convert the plain text message into the web encrypted frame. Mainly, if it provides confidentiality, then we are sending it in an encrypted manner. This is the encrypted web frame format. We are having the plain text. How we are sending the plain text means message from the plus the cyclic redundancy check, that is XORed with the key stream. Then we are getting the cipher text. In the cipher text, we are adding the initialization vector, appending with the initialization vector. Then only we are transmitting the cipher text to the destination by adding the initialization vector using this encrypted web frame. Next, RC4 key stream XORed with the plain text. How the encryption process happens. See here, we are having the initialization vector plus key that accesses seed, and it is given as input to the RC4. Then the key stream is generated, that is XORed with the plain text to give the cipher text. The main thing is in the RC4, the input is initialization vector plus key that accesses seed. Not only the key, initialization vector plus the key. These are some of the web components, that is initialization vector. We know it is a dynamic 24-bit value. It is chosen randomly by the transmitter wireless network interface, and the possible keys are 16.7 million possible keys, that is 2 power 24 keys are used. Then coming to the shared secret key, it is 40 bits long. There is 5 ASCII characters are used when 64 key is used. Then 104 bits long when 128-bit key is used as a shared secret key. Then in the RC4 algorithm, it consists of two parts. One is the key scheduling algorithm and another one is the pseudo-random generation algorithm. In the key scheduling algorithm, it involves creating a scrambled state array, and the state array will be used as input in the second phase called the pseudo-random generation algorithm. And in the pseudo-random number generation algorithm, the state array from the key scheduling algorithm process is used to generate a final key stream, and each byte of the key stream generated is then XORed with the corresponding plaintext byte to produce the desired ciphertext. So it's all a general procedure only. Generally we are making some operation, that is we are using any algorithm or any function. The input to the function is the plaintext as well as the key. So what function we are using here? We are only performing the XOR operation. But before that, in order to create a key stream, we are doing some operation to have in a secured manner. For that only, not just directly we are using the key stream alone. There we are adding some more things with the key stream. Then only we are making that with the key, not the key stream. Then we are generating the key stream, and with the key stream we are XORing the plaintext and we are getting the ciphertext. So here we are having the integrity check value, that is the CRC32 integrity check. How the XOR operation is performed means plaintext plus the key stream you are getting the ciphertext, then ciphertext plus the key stream you are getting the plaintext. With plaintext XOR ciphertext we are getting the key stream. So this way only this wired equivalent privacy works. So this is the pictorial representation of how the wired equivalent privacy works. That is, we know original unencrypted packet plus the checksum is added. How we are computing the checksum means from the original unencrypted packet only we are adding the checksum. Here for the input to the RC4 is the initialization vector as well as the key, that is XORed with the original unencrypted packet plus the checksum. Then we are getting the initialization packet. So in the encrypted packet. So in the encrypted packet, what we are doing? We are just adding the initialization vector with the encrypted packet, that is ciphertext. Then only we are sending. So whatever we have seen numerically, the same thing only here it is represented as in a pictorial form. The encryption process, how it is done means the initialization vector, then the WP key is concatenated, that forms the seed and it is given to the RC4 pseudo random number generator. So from that the key stream is formed. So initialization vector plus the key, it is given to the RC4, then only the key stream is generated. And in the key stream we are XORing the plaintext. Before XORing the plaintext, what we are doing is we are just getting the cyclic redundancy check of the plaintext. Then plaintext is concatenated with the cyclic redundancy check, that we are calling it as integrity check value, that is XORed. Key stream plus this value is XORed, then we are getting the ciphertext. In the ciphertext we are just appending the initialization vector as well. That's very, very important. So the same method is explained many times in different manner. That's all. Then coming to the decryption process, we are having the ciphertext as well as the initialization vector. So directly we are taking the initialization vector, then we are having the web key that is concatenated and is given to the RC4 pseudo random number generator to form the key stream. Then the ciphertext and the key stream is XORed and we are getting the plain text. So we have already seen if the plain text is XORed with the key stream, you are getting the ciphertext. And if the ciphertext is XORed with the key stream, you are getting the plain text. If the plain text is XORed with the ciphertext, we are getting the key stream. The three steps are the main things in the wired equivalent privacy. That is the working principle of wired equivalent privacy. Next is the web authentication. Here the station sends an authentication request to the access point, and the access point sends challenge text to the station. Then the station uses the configured 64-bit or 128-bit default key to encrypt the challenge text, and it sends the later to the access point, and the access point decrypts the encrypted text using its configured web key that corresponds to the station's default key. Then the access point compares the decrypted text with the original challenge text, and if the decrypted text matches the original challenge text, then only the access point and the station share the web key, and the access point authenticates the station. So this way only authentication happens. The station connects to the network. If it is authenticated, then only the station has to be connected to the network. So authentication process, this wired equivalent privacy is working in this principle in order to check the authentication. So this is the pictorial representation. We are having the wireless station and the access point. First, authentication request is sent from wireless station to the access point. Then the access point is sending the challenge, that is the text packet. Then the wireless station is sending the challenge response, that is the encrypted text packet. Then finally the access point is just sending the confirm success, that is it is decrypting the text packet using web key value and verify whether it is same as the original packet. Then authentication happens in a correct manner. If authentication is successful, then only they can transfer the or exchange the messages. There is a well documented vulnerability with this shared key authentication, and this authentication process leaks information about the key stream. But it is possible to derive the key stream used for the handshake by capturing the challenge frames in this shared key authentication. And many times the shared key authentication is regarded as an insecure thing, because the problem is that a monitoring attacker can observe both challenge and the encrypted response. So how we are determining whether it is insecure or not means, we are determining the RC4 stream used to encrypt the response. Then we use that stream to encrypt any challenge received in this way. Some of the web flaws and vulnerabilities include, there are weak keys associated with this web, that is it allows an attacker to discover the default key being used by the access point and client stations, and this enables an attacker to decrypt all messages being sent over the encrypted channel. So if any attacker wants to perform any attack means, the attacker has to exploit the access point in order to get all the contact details of the wireless devices connected to the access point. And in the initialization vector can be reused, and it is of small size, that is there are 2 power 24 different IVs are there on a busy network. The initialization vector will surely be reused, and if the default key has not been changed, and the original message can be retrieved relatively easier manner. With this initialization vector reuse, it is possible to determine the key streams and hence enable an attacker to force the packets obtaining the access to the wireless LAN. If this web is using 40-bit long key, then it will need more protection from attacks as compared to the 128-bit long web key. Hence, both are very weak, unable to provide the security to Wi-Fi networks. So, it uses some weak authentication algorithm, and it uses some weak data encapsulation method. So, the use of improper integrity algorithm, that is ERC32 only, makes the web flaws, and it is vulnerable to some attacks. So in this presentation, we have discussed about the introduction to IEEE 802.11. It is for wireless LAN, and we have discussed about the Wi-Fi Alliance and IEEE 802 protocol architecture. Then how we are providing security for this 802.11. Then wired equivalent privacy. Then we have discussed about the web components, how web works, web authentication, web flaws, and vulnerabilities. So we completed the 5th unit, and the 6th unit is about intrusion detection, that already we have completed. Thank you.